Chapter 3. Energy bands and charge carriers in semiconductors. Objectives. 1. Understand conduction and valence energy bands, and how band gaps are formed. 2. Appreciate the idea of doping in semiconductors. 3. Use the density of states and Fermi-Dirac statistics to calculate carrier concentrations. 4. Calculate drift currents in an electric field in terms of carrier mobility, and how mobility is affected by scattering. 5. Discuss the idea of effective masses. In this chapter we begin to discuss the specific mechanisms by which current flows in a solid. In examining these mechanisms we shall learn why some materials are good conductors of electric current, whereas others are poor conductors. We shall see how the conductivity of a semiconductor can be varied by changing the temperature or the number of impurities. These fundamental concepts of charge transport form the basis for later discussions of solid-state device behavior. In Chapter 2 we found that electrons are restricted to sets of discrete energy levels within atoms. Large gaps exist in the energy scale in which no energy states are available. In a similar fashion, electrons in solids are restricted to certain energies and are not allowed at other energies. The basic difference between the case of an electron in a solid and that of an electron in an isolated atom is that in the solid the electron has a range, or band, of available energies. The discrete energy levels of the isolated atom spread into bands of energies in the solid because in the solid the wave functions of electrons in neighboring atoms overlap, and an electron is not necessarily localized at a particular atom. Thus, for example, an electron in the outer orbit of one atom feels the influence of neighboring atoms, and its overall wave function is altered. Naturally, this influence affects the potential energy term and the boundary conditions in the Schrödinger equation, and we would expect to obtain different energies in the solution. Usually, the influence of neighboring atoms on the energy levels of a particular atom can be treated as a small perturbation, giving rise to shifting and splitting of energy states into energy bands. Bonding forces in solids. The interaction of electrons in neighboring atoms of a solid serves the very important function of holding the crystal together. For example, alkali halides such as sodium chloride are typified by ionic bonding. In the sodium chloride lattice, each sodium atom is surrounded by 6 nearest neighbor chlorine atoms, and vice versa. 4 of the nearest neighbors are evident in the two-dimensional representation shown in Fig 3.1a. The electronic structure of sodium, Z=11, is neon 3s1, and class, Z=17, has the structure neon 3s23p5. In the lattice each sodium atom gives up its outer 3s electron to a chlorine atom, so that the crystal is made up of ions with the electronic structures of the inert atoms neon and argon. Argon has the electronic structure neon 3s23p6. However, the ions have net electric charges after the electron exchange. The sodium positive ion has a net positive charge, having lost an electron, and the chloride ion has a net negative charge, having gained an electron. Each sodium positive ion exerts an electrostatic attractive force upon its 6 negative chlorine neighbors, and vice versa. These coulombic forces pull the lattice together until a balance is reached with repulsive forces. A reasonably accurate calculation of the atomic spacing can be made by considering the ions as hard spheres being attracted together, example 1.1. An important observation in the sodium chloride structure is that all electrons are tightly bound to atoms. Once the electron exchanges have been made between the sodium and chlorine atoms to form the sodium positive and chlorine negative ions, the outer orbits of all atoms are completely filled. Since the ions have the closed shell configurations of the inert atoms neon and argon, there are no loosely bound electrons to participate in current flow. As a result, sodium chloride is a good insulator. In a metal atom the outer electronic shell is only partially filled, usually by no more than 3 electrons. We have already noted that the alkali metals, for example, sodium, have only 1 electron in the outer orbit. This electron is loosely bound and is given up easily in ion formation. This accounts for the great chemical activity in the alkali metals, as well as for their high electrical conductivity. In the metal, the outer electron of each alkali atom is contributed to the crystal as a whole, so that the solid is made up of ions with closed shells immersed in a sea of free electrons. The forces holding the lattice together arise from an interaction between the positive ion cores and the surrounding free electrons. This is one type of metallic bonding. Obviously, there are complicated differences in the bonding forces for various metals, as evidenced by the wide range of melting temperatures, 234 K for mercury, 3643 K for wolfram. However, the metals have the sea of electrons in common, and these electrons are free to move about the crystal under the influence of an electric field. A third type of bonding is exhibited by the diamond lattice semiconductors. We recall that each atom in the germanium, silicon, or carbon diamond lattice is surrounded by 4 nearest neighbors, each with 4 electrons in the outer orbit. In these crystals, each atom shares its valence electrons with its 4 neighbors, Fig 3.1b. Bonding between nearest neighbor atoms is illustrated in the diamond lattice diagram of Fig 1.9. The bonding forces arise from a quantum mechanical interaction between the shared electrons. This is known as covalent bonding. Each electron pair constitutes a covalent bond. In the sharing process, it is no longer relevant to ask which electron belongs to a particular atom, both belong to the bond. The 2 electrons are indistinguishable, except that they must have opposite spin to satisfy the Pauli exclusion principle. Covalent bonding is also found in certain molecules, such as H2. As in the case of the ionic crystals, no free electrons are available to the lattice in the covalent diamond structure of Fig 3.1b. By this reasoning, germanium and silicon should also be insulators. However, we have pictured an idealized lattice at 0K in this figure. As we shall see in subsequent sections, an electron can be thermally or optically excited out of a covalent bond and thereby become free to participate in conduction. This is an important feature of semiconductors. Compound semiconductors such as gallium arsenide have mixed bonding, in which both ionic and covalent bonding forces participate. Some ionic bonding is to be expected in a crystal such as gallium arsenide because of the difference in placement of the gallium and arsine atoms in the periodic table. The ionic character of the bonding becomes more important as the atoms of the compound become further separated in the periodic table, as in the 2,6 compounds. Such electronic structure, and specifically the idea that the outermost valence shell is complete if it has a stable set of 8 electrons, neon, argon, krypton, is the basis of most of chemistry and many of the semiconducting properties. Energy bands. As isolated atoms are brought together to form a solid, various interactions occur between neighboring atoms, including those described in the preceding section. The forces of attraction and repulsion between atoms will find a balance at the proper interatomic spacing for the crystal. In the process, important changes occur in the electron energy level configurations, and these changes result in the varied electrical properties of solids. In Fig 2.8, we showed the orbital model of a silicon atom, along with the energy levels of the various electrons in the Coulombic potential well of the nucleus. Let us focus on the outermost shell or valence shell, n = 3, where 2 3s and 2 3p electrons interact to form the 4 hybridized sp3 electrons when the atoms are brought close together. In Fig 3.2, we schematically show the Coulombic potential wells of 2 atoms close to each other, along with the wave functions of 2 electrons centered on the 2 nuclei. By solving the Schrödinger equation for such an interacting system, we find that the composite 2 electron wave functions are linear combinations of the individual atomic orbitals, LCAO. The odd or anti-symmetric combination is called the antibonding orbital, while the even or symmetric combination is the bonding orbital. It can be seen that the bonding orbital has a higher value of the wave function, and therefore the electron probability density, than the antibonding state in the region between the 2 nuclei. This corresponds to the covalent bond between the atoms. Fundamental particles in nature have either integer spin and are called bosons, for example, photons, or half-integer spin and are known as fermions, for example, electrons. The quantum mechanical wave function of the electron has a spatial, or orbital, part and a spin-dependent part. It can be shown that Fermion wave functions of a multi-electron system must be antisymmetric. When the spatial part is symmetric, the electron spins must be antiparallel, and vice versa. Hence, the two electrons in the bonding orbital have opposite spins, while those in the antibonding state have parallel spins. This explains the Pauli exclusion principle. When we try to put two electrons into a quantum state, they must have opposite spins. Parallel spin electrons quantum mechanically repel each other, as seen for the antisymmetric orbital. This should not be confused with Coulomb repulsion of the electrons. Later on in Chapter 10, we will see that these concepts have important ramifications for nanoelectronics. To determine the energy levels of the bonding and the antibonding states, it is important to recognize that in the region between the two nuclei the Coulombic potential energy V, R, is lowered, solid line in Fig 3.2, compared to isolated atoms, dashed lines. It is easy to see why the potential energy would be lowered in this region, because an electron here would be attracted by two nuclei, rather than just one. For the bonding state the electron probability density is higher in this region of lowered potential energy than for the antibonding state. As a result, the original isolated atomic energy level would be split into two, a lower bonding energy level and a higher antibonding level. It is the lowering of the energy of the bonding state that gives rise to cohesion of the crystal. For even smaller interatomic spacings, the energy of the crystal goes up because of repulsion between the nuclei, and other electronic interactions. Since the probability density is given by the square of the wave function, if the entire wave function is multiplied by -1, it does not lead to a different LCAO. The important point to note in this discussion is that the number of distinct LCAO, and the number of distinct energy levels, depends on the number of atoms that are brought together. The lowest energy level corresponds to the totally symmetric LCAO, the highest corresponds to the totally antisymmetric case, and the other combinations lead to energy levels in between. Qualitatively, we can see that as atoms are brought together, the application of the Pauli exclusion principle becomes important. When two atoms are completely isolated from each other so that there is no interaction of electron wave functions between them, they can have identical electronic structures. As the spacing between the two atoms becomes smaller, however, electron wave functions begin to overlap. The exclusion principle dictates that no two electrons in a given interacting system may have the same quantum state, thus there must be at most one electron per level after there is a splitting of the discrete energy levels of the isolated atoms into new levels belonging to the pair rather than to individual atoms. In a solid, many atoms are brought together, so that the split energy levels form essentially continuous bands of energies. As an example, Fig 3.3 illustrates the imaginary formation of a silicon crystal from isolated silicon atoms. Each isolated silicon atom has an electronic structure 1s22 s22 p63 s23 p2 in the ground state. Each atom has available 2 1 states, 2 2 states, 6 2p states, 2 3 states, 6 3p states, and higher states, see tables 2 1 and 2 2. If we consider n atoms, there will be 2n, 2n, 6n, 2n, and 6n states of type 1s, 2s, 2p, 3s, and 3p, respectively. As the interatomic spacing decreases, these energy levels split into bands, beginning with the outer, n equal 3, shell. As the 3s and 3p bands grow, they merge into a single band composed of a mixture of energy levels. This band of 3s 3p levels contains 8n available states. As the distance between atoms approaches the equilibrium interatomic spacing of silicon, this band splits into two bands separated by an energy gap e.g. The upper band, called the conduction band, contains 4n states, as does the lower, valence, band. Thus, apart from the low-lying and tightly bound core levels, the silicon crystal has two bands of available energy levels separated by an energy gap e.g. wide, which contains no allowed energy levels for electrons to occupy. This gap is sometimes called a forbidden band, since in a perfect crystal it contains no electron energy states. We should pause at this point and count electrons. The lower 1s band is filled with the 2n electrons which originally resided in the collective 1 states of the isolated atoms. Similarly, the 2s band and the 2p bands will have 2n and 6n electrons in them, respectively. However, there were 4n electrons in the original isolated n equal 3 shells, 2n in 3 states and 2n in 3p states. Energy levels in Si as a function of interatomic spacing. The core levels, n equal 1, 2, in Si are completely filled with electrons. At the actual atomic spacing of the crystal, the 2n electrons in the 3 subshell and the 2n electrons in the 3p subshell undergo sp3 hybridization, and all end up in the lower 4n states, valence band, while the higher lying 4n states, conduction band, are empty, separated by a band gap. These 4n electrons must occupy states in the valence band or the conduction band in the crystal. At 0K the electrons will occupy the lowest energy states available to them. In the case of the Si crystal, there are exactly 4n states in the valence band available to the 4n electrons. Thus at 0K, every state in the valence band will be filled, while the conduction band will be completely empty of electrons. As we shall see, this arrangement of completely filled and empty energy bands has an important effect on the electrical conductivity of the solid. Metals, semiconductors, and insulators. Every solid has its own characteristic energy band structure. This variation in band structure is responsible for the wide range of electrical characteristics observed in various materials. The silicon band structure of Fig 3.3, for example, can give a good picture of why silicon in the diamond lattice is a good insulator. To reach such a conclusion, we must consider the properties of completely filled and completely empty energy bands in the current conduction process. Before discussing the mechanisms of current flow in solids further, we can observe here that for electrons to experience acceleration in an applied electric field, they must be able to move into new energy states. This implies there must be empty states, allowed energy states which are not already occupied by electrons, available to the electrons. For example, if relatively few electrons reside in an otherwise empty band, ample unoccupied states are available into which the electrons can move. On the other hand, the silicon band structure is such that the valence band is completely filled with electrons at 0K and the conduction band is empty. There can be no charge transport within the valence band, since no empty states are available into which electrons can move. There are no electrons in the conduction band, so no charge transport can take place there either. Thus silicon at 0K has a high resistivity typical of insulators. Semiconductor materials at 0K have basically the same structure as insulators, a filled valence band separated from an empty conduction band by a band gap containing no allowed energy states, Fig 3.4. The difference lies in the size of the band gap, e.g., which is much smaller in semiconductors than in insulators. For example, the semiconductor Si has a band gap of about 1.1 eV compared with 5 eV for diamond. The relatively small band gaps of semiconductors, Appendix 3, allow for excitation of electrons from the lower, valence, band to the upper, conduction, band by reasonable amounts of thermal or optical energy. For example, at room temperature a semiconductor with a 1 eV band gap will have a significant number of electrons excited thermally across the energy gap into the conduction band, whereas an insulator with energy gap equal 10 eV will have a negligible number of such excitations. Thus an important difference between semiconductors and insulators is that the number of electrons available for conduction can be increased greatly in semiconductors by thermal or optical energy. In metals the bands either overlap or are only partially filled. Thus electrons and empty energy states are intermixed within the bands so that electrons can move freely under the influence of an electric field. As expected from the metallic band structures of Fig 3.4, metals have a high electrical conductivity. Direct and indirect semiconductors. The thought experiment of section 3.1.2, in which isolated atoms were brought together to form a solid, is useful in pointing out the existence of energy bands and some of their properties. Other techniques are generally used, however, when quantitative calculations are made of band structures. In a typical calculation, a single electron is assumed to travel through a perfectly periodic lattice. The wave function of the electron is assumed to be in the form of a plane wave1 moving, for example, in the x direction with propagation constant k, also called a wave vector. The space-dependent wave function for the electron is where the function u, kx, x, modulates the wave function according to the periodicity of the lattice. Such wave functions are called Bloch functions after the physicist Felix Bloch. In such a calculation, allowed values of energy can be plotted versus the propagation constant k. Since the periodicity of most lattices is different in various directions, the E, K diagram must be plotted for the various crystal directions, and the full relationship between E and K is a complex surface which should be visualized in 3 dimensions. The band structure of gallium arsenide has a minimum in the conduction band and a maximum in the valence band for the same K value, K equals 0. On the other hand, Si has its valence band maximum at a different value of K than its conduction band minimum. Thus an electron making a smallest energy transition from the conduction band to the valence band in gallium arsenide can do so without a change in K value. On the other hand, a transition from the minimum point in the Si conduction band to the maximum point of the valence band requires some change in K. Thus there are 2 classes of semiconductor energy bands, direct and indirect, Fig 3.5. We can show that an indirect transition, involving a change in K, requires a change of momentum for the electron. The direct and indirect semiconductors are identified in Appendix 3. In a direct semiconductor such as gallium arsenide, an electron in the conduction band can fall to an empty state in the valence band, giving off the energy difference e.g. as a photon of light. On the other hand, an electron in the conduction band minimum of an indirect semiconductor such as Si cannot fall directly to the valence band maximum but must undergo a momentum change as well as changing its energy. For example, it may go through some defect state, ET, within the band gap. We shall discuss such defect states in sections 4.2.1 and 4.3.2. In an indirect transition which involves a change in K, part of the energy is generally given up as heat to the lattice rather than as an emitted photon. This difference between direct and indirect band structures is very important for deciding which semiconductors can be used in devices requiring light output. For example, semiconductor light emitters and lasers, Chapter 8, generally must be made of materials capable of direct band-to-band transitions or of indirect materials with vertical transitions between defect states. Band diagrams such as those shown in Fig 3.5 are cumbersome to draw in analyzing devices, and do not provide a view of the variation of electron energy with distance in the sample. Therefore, in most discussions we shall use simple band pictures such as those shown in Fig 3.4, remembering that electron transitions across the band gap may be direct or indirect. Variation of energy bands with alloy composition. Arsenide 3,5 ternary and quaternary alloys are varied over their composition ranges, see sections 1.2.4 and 1.4.1, their band structures change. For example, Fig 3.6 illustrates the band structure of gallium arsenide and aluminum arsenide, and the way in which the bands change with composition X in the ternary compound aluminum X gallium 1X arsenide. The binary compound gallium arsenide is a direct material, with a band gap of 1.43 eV at room temperature. For reference, we call the direct, K equals 0, conduction band minimum. There are also 2 higher-lying indirect minima in the gallium arsenide conduction band, but these are sufficiently far above that few electrons reside there. We discuss an important exception in Chapter 10 in which high field excitation of electrons into the indirect minima leads to the gun effect. We call the lowest lying gallium arsenide indirect minimum L and the other X. In aluminum arsenide the direct minimum is much higher than the indirect X minimum, and this material is therefore indirect with a band gap of 2.16 eV at room temperature. Figure 3.6. Variation of direct and indirect conduction bands in aluminum gallium arsenide as a function of composition. A. The E. K. Diagram for gallium arsenide, showing 3 minima in the conduction band. B. Aluminum arsenide band diagram. C. Positions of the 3 conduction band minima in aluminum x gallium 1x arsenide as x varies over the range of compositions from gallium arsenide, x equals 0, to aluminum arsenide, x equal 1. The smallest band gap, e.g., shown in color, follows the direct band to x equals 0.38, and then follows the indirect x band. In the ternary alloy aluminum x gallium x arsenide, all of these conduction band minima move up relative to the valence band as the composition x varies from 0, GAAS, to 1, ALAS. However, the indirect minimum x moves up less than the others, and for compositions above about 38% aluminum this indirect minimum becomes the lowest lying conduction band. Therefore, the ternary alloy aluminum gallium arsenide is a direct semiconductor for aluminum compositions on the column 3 sublattice up to about 38%, and is an indirect semiconductor for higher aluminum mole fractions. The band gap energy e.g. is shown in color on Fig 3.6c. The variation of energy bands for the ternary alloy gallium arsenide 1x phosphide X is generally similar to that of aluminum gallium arsenide shown in Fig 3.6. Gallium arsenide phosphate is a direct semiconductor from gallium arsenide to about gallium arsenide 55P45 and is indirect from this composition to gallium phosphide, see Fig 8.11. This material is often used in visible light-emitting diodes. Since light emission is most efficient for direct materials, in which electrons can drop from the conduction band to the valence band without changing K, and therefore momentum, light-emitting diodes in gallium arsenide phosphide are generally made in materials grown with a composition less than X equals 0.45. For example, most red light-emitting diodes in this material are made at about X equals 0.4, where the minimum is still the lowest lying conduction band edge, and where the photon resulting from a direct transition from this band to the valence band is in the red portion of the spectrum, about 1.9 electron volts. The use of impurities to enhance radiative recombination in indirect material will be discussed in section 8.2. The mechanism of current conduction is relatively easy to visualize in the case of a metal. The metal atoms are embedded in a sea of relatively free electrons, and these electrons can move as a group under the influence of an electric field. This free electron view is oversimplified, but many important conduction properties of metals can be derived from just such a model. However, we cannot account for all of the electrical properties of semiconductors in this way. Since the semiconductor has a filled valence band and an empty conduction band at 0 K, we must consider the increase in conduction band electrons by thermal excitations across the band gap as the temperature is raised. In addition, after electrons are excited to the conduction band, the empty states left in the valence band can contribute to the conduction process. The introduction of impurities has an important effect on the energy band structure and on the availability of charge carriers. Thus there is considerable flexibility in controlling the electrical properties of semiconductors. Electrons and holes. As the temperature of a semiconductor is raised from 0 K, some electrons in the valence band receive enough thermal energy to be excited across the band gap to the conduction band. The result is a material with some electrons in an otherwise empty conduction band and some unoccupied states in an otherwise filled valence band, Fig 3.7. 2. For convenience, an empty state in the valence band is referred to as a hole. If the conduction band electron and the hole are created by the excitation of a valence band electron to the conduction band, they are called an electron-hole pair, abbreviated EHP. After excitation to the conduction band, an electron is surrounded by a large number of unoccupied energy states. For example, the equilibrium number of electron-hole pairs in pure silicon at room temperature is only about 10 billion electron-hole pair per cubic centimeter, compared to the silicon atom density of 5*1022 atoms per cubic centimeter. Thus the few electrons in the conduction band are free to move about via the many available empty states. The corresponding problem of charge transport in the valence band is somewhat more complicated. However, it is possible to show that the effects of current in a valence band containing holes can be accounted for by simply keeping track of the holes themselves. In a filled band, all available energy states are occupied. For every electron moving with a given velocity, there is an equal and opposite electron motion elsewhere in the band. If we apply an electric field, the net current is zero because for every electron j moving with velocity vj there is a corresponding electron j with velocity vj. Figure 3.8 illustrates this effect in terms of the electron energy versus wave vector plot for the valence band. Since k is proportional to electron momentum, it is clear the two electrons have oppositely directed velocities. With n electron/centimeter 3 in the band we express the current density using a sum over all of the electron velocities, and including the charge q on each electron. In a unit volume, filled band. Now if we create a hole by removing the jth electron, the net current density in the valence band involves the sum over all velocities, minus the contribution of the electron we have removed. Electron missing but the first term is 0, from EQ 3 to A. Thus the net current is plus QVJ. In other words, the current contribution of the hole is equivalent to that of a positively charged particle with velocity Vj, that of the missing electron. Of course, the charge transport is actually due to the motion of the new uncompensated electron, J. Its current contribution, Q, Vj, is equivalent to that of a positively charged particle with velocity plus Vj. For simplicity, it is customary to treat empty states in the valence band as charge carriers with positive charge and positive mass. A simple analogy may help in understanding the behavior of holes. If we have two bottles, one completely filled with water and one completely empty, we can ask ourselves, will there be any net transport of water when we tilt the bottles? The answer is no. In the case of the empty bottle, the answer is obvious. In the case of the completely full bottle also, there cannot be any net motion of water because there is no empty space for water to move into. Similarly, an empty conduction band completely devoid of electrons or a valence band completely full of electrons cannot give rise to a net motion of electrons, and thus to current conduction. Next, we imagine transferring some water droplets from the full bottle into the empty bottle, leaving behind some air bubbles, and ask ourselves the same question. Now when we tilt the bottles there will be net transport of water, the water droplets will roll downhill in one bottle and the air bubbles will move uphill in the other. Similarly, a few electrons in an otherwise empty conduction band move opposite to an electric field, while holes in an otherwise filled valence band move in the direction of the field. The bubble analogy is imperfect, but it may provide a physical feel for why the charge and mass of a hole have opposite signs from those of an electron. In all the following discussions we shall concentrate on the electrons in the conduction band and on the holes in the valence band. We can account for the current flow in a semiconductor by the motion of these two types of charge carriers. We draw valence and conduction bands on an electron energy scale E, as in Fig 3.8. However, we should remember that in the valence band, hole energy increases oppositely to electron energy, because the two carriers have opposite charge. Thus hole energy increases downward in Fig 3.8 and holes, seeking the lowest energy state available, are generally found at the top of the valence band. In contrast, conduction band electrons are found at the bottom of the conduction band. It would be instructive to compare the E, K band diagrams with the simplified band diagrams that are used for routine device analysis, Fig 3.9. As discussed in examples 3.1 and 3.2, an E, K diagram is a plot of the total electron energy, potential plus kinetic, as a function of the crystal direction-dependent electron wave vector, which is proportional to the momentum and therefore the velocity, at some point in space. Hence, the bottom of the conduction band corresponds to zero electron velocity, or kinetic energy, and simply gives us the potential energy at that point in space. For holes, the top of the valence band corresponds to zero kinetic energy. For simplified band diagrams, we plot the edges of the conduction and valence bands, i.e., the potential energy, as a function of position in the device. Energies higher in the band correspond to additional kinetic energy of the electron. Also, the fact that the band edge corresponds to the electron potential energy tells us that the variation of the band edge in space is related to the electric field at different points in the semiconductor. We will show this relationship explicitly in section 4.4.2. Figure 3.9. Superimposition of the E, K, band structure on the E versus position simplified band diagram for a semiconductor in an electric field. Electron energies increase going up, while hole energies increase going down. Similarly, electron and hole wave vectors point in opposite directions and these charge carriers move opposite to each other, as shown. In Fig 3.9, an electron at location A sees an electric field given by the slope of the band edge, potential energy, and gains kinetic energy, at the expense of potential energy, by moving to point B correspondingly. In the E, K, diagram, the electron starts at K equals 0, but moves to a non-zero wave vector kilobytes. The electron then loses kinetic energy to heat by scattering mechanisms, discussed in section 3.4.3, and returns to the bottom of the band at B. The slopes of the E, X, band edges at different points in space reflect the local electric fields at those points. Hence, if the electric field between A and B were not constant, as shown in Fig 3.9, the slope of the band edge would also not be constant but vary at each point reflecting the magnitude and direction of the local electric field. In practice, the electron may lose its kinetic energy in stages by a series of scattering events, as shown by the colored dashed lines. In a long semiconductor bar, conduction band electrons come in from the left in the positive x direction with a kinetic energy of 3 eV. They move from location A to B to C to D. Between A and B, the electric field is 0, between locations B and C, there is a linearly varying voltage increase of 4V, between C and D, the field is again 0. Assuming no scattering, sketch a simplified band diagram describing the motion of these electrons. Assuming that these electrons can be described as plane waves, with a free electron mass, write down the wave function of the electrons at D. Leave your result in terms of an arbitrary normalization constant. Draw a band diagram and give the wave function at D in terms of the normalization constant. Effective mass. The electrons in a crystal are not completely free, but instead interact with the periodic potential of the lattice. As a result, their wave particle motion cannot be expected to be the same as for electrons in free space. Thus, in applying the usual equations of electrodynamics to charge carriers in a solid, we must use altered values of particle mass. In doing so, we account for most of the influences of the lattice, so that the electrons and holes can be treated as almost free carriers in most computations. The calculation of effective mass must take into account the shape of the energy bands in three-dimensional K-space, taking appropriate averages over the various energy bands. Find the E, K, relationship for a free electron and relate it to the electron mass. From example 2.2, the electron momentum is P equal mv equal uk. Thus the electron energy is parabolic with wave vector k. The electron mass is inversely related to the curvature, second derivative, of the E, K, relationship, since d2e dk2 equal u2m. Although electrons in solids are not free, most energy bands are close to parabolic at their minima, for conduction bands, or maxima, for valence bands. We can also approximate effective mass near those band extrema from the curvature of the band. The effective mass of an electron in a band with a given E, K, relationship is found in example 3.2 to be. Thus the curvature of the band determines the electron effective mass. For example, in Fig 3.6 it is clear that the electron effective mass in GaAs is much smaller in the direct conduction band, strong curvature, than in the L or X minima, weaker curvature, smaller value in the denominator of the m** expression. A particularly interesting feature of figs 3.5 and 3.6 is that the curvature of d2e dk2 is positive at the conduction band minima, but is negative at the valence band maxima. Thus, the electrons near the top of the valence band have negative effective mass, according to EQ. 3.3. Valence band electrons with negative charge and negative mass move in an electric field in the same direction as holes with positive charge and positive mass. As discussed in section 3.2.1, we can fully account for charge transport in the valence band by considering hole motion. For a band centered at k equals 0, such as the band in gallium arsenide, the E-K relationship near the minimum is usually parabolic. Comparing this relation to EQ 3.3 indicates that the effective mass m* is constant in a parabolic band. On the other hand, many conduction bands have complex E-K relationships that depend on the direction of electron transport with respect to the principal crystal directions. In this case, the effective mass is a tensor quantity. However, we can use appropriate averages over such bands in most calculations. Figure 3.10 shows the band structures for silicon and gallium arsenide viewed along two major directions. While the shape is parabolic near the band edges, as indicated in figure 3.5 and example 3.2, there are significant nonparabolicities at higher energies. The energies are plotted along the high symmetry 111 and 100 directions in the crystal. The k equals 0 point is denoted as. When we go along the 100 direction, we reach a valley near x, while we reach the L valley along the 111 direction. Since the energies are plotted along different directions, the curves do not look symmetric. The valence band maximum in most semiconductors is at the point. It has three branches: the heavy hole band with the smallest curvature, a light hole band with a larger curvature, and a split-off band at a different energy. We notice that for GAAS the conduction band minimum and the valence band maximum are both at k equals 0, therefore it is direct band gap. Silicon, on the other hand, has 6 equivalent conduction minima at x along the 6 equivalent 81009 directions, therefore, it is indirect. Figure 3.10. Realistic band structures in semiconductors: A. Conduction and valence bands in silicon and gallium arsenide along 111 and 100, B. Ellipsoidal constant energy surface for silicon, near the 6 conduction band minima. Along the x directions. From Kelikowski and Cohen, Ph.Ys. Rev. B14, 556, 1976. Figure 3.10b shows the constant energy surface for electrons in one of the 6 conduction bands for silicon. The way to relate these surfaces to the band structures shown in Fig 3.10 is to consider a certain value of energy, and determine all the k vectors in 3 dimensions for which we get this energy. We find that for silicon we have 6 cigar-shaped ellipsoidal equi-energy surfaces near the conduction band minima along the 6 equivalent x directions, with a longitudinal effective mass, milliliter, along the major axis, and 2 transverse effective masses, mount, along the minor axis. For gallium arsenide, the conduction band is more or less spherical for low energies. On the other hand, we have warped spherical surfaces in the valence band. The importance of these surfaces will be clear in sections 3.3.2 and 3.4.1 when we consider different types of effective masses in semiconductors. In any calculation involving the mass of the charge carriers, we must use effective mass values for the particular material involved. In all subsequent discussions, the electron effective mass is denoted by m*n and the hole effective mass by m*p. The n subscript indicates the electron as a negative charge carrier, and the p subscript indicates the hole as a positive charge carrier. There is nothing mysterious about the concept of an effective mass, m*n, and about the fact that it is different in different semiconductors. Indeed, the true mass of an electron, m, is the same in silicon, germanium, or gallium arsenide is the same as for a free electron in vacuum. To understand why the effective mass is different from the true mass, consider Newton's second law, which states that the time rate of change of momentum is the force. dp/dt equal d, mv/dt equal force, 35a. An electron in a crystal experiences a total force Fint plus Vext, where Fint is the collection of internal periodic crystal forces, and Vext is the externally applied force. It is inefficient to solve this complicated problem involving the periodic crystal potential, which is obviously different in different semiconductors, every time we try to solve a semiconductor device problem. It is better to solve the complicated problem of carrier motion in the periodic crystal potential just once, and encapsulate that information in what is called the band structure, E, K, whose curvature gives us the effective mass, m*n. The electron then responds to external forces with this new m*n. For carriers near the parabolic band extrema where the effective mass is as described, Newton's law is then written as d m*nv dt equal Vext, 35b. This is clearly an enormous simplification compared to the more detailed problem. Obviously, the periodic crystal forces depend on the details of a specific semiconductor, therefore, the effective mass is different in different materials. The velocity of the electron, v, is the group velocity of a quantum mechanical electron wave packet that we introduced in section 1.5. If E, K, is given by a simple parabolic relation as in EQ 3,4, we see that. But in general, the carrier velocity is proportional to the slope of the band structure. So, for instance, if an electron is at the SI conduction band minimum, Fig 310a, its velocity is 0, even though UK is non-zero here. For simple parabolic E, K, as in EQ 3,4, EQ 3,5b, can then also be written as. Since Vext is not the total force imposed on the electron, clearly UK cannot be the true momentum. It is called the crystal momentum or quasi-momentum. Equations 3,5c and 3,5d are the fundamental equations governing carrier motion in semiconductors, and are known as semi-classical dynamics. Once we determine the band curvature effective mass components from the orientation-dependent, E, K, we have to combine them appropriately for different types of calculations. We shall see in section 3.3.2 that when we are interested in determining the numbers of carriers in the bands, we have to use a density of states effective mass by taking the geometric mean of the band curvature effective masses, and the number of equivalent band extrema. On the other hand, we will find in section 3.4.1 that in problems involving the motion of carriers, one must take the harmonic mean of the band curvature effective masses to get the conductivity effective mass. Intrinsic material: a perfect semiconductor crystal with no impurities or lattice defects is called an intrinsic semiconductor. In such material there are no charge carriers at 0 K, since the valence band is filled with electrons and the conduction band is empty. At higher temperatures electron-hole pairs are generated as valence band electrons are excited thermally across the band gap to the conduction band. These electron-hole pairs are the only charge carriers in intrinsic material. The generation of electron-hole pairs can be visualized in a qualitative way by considering the breaking of covalent bonds in the crystal lattice, Fig 311. If one of the Si valence electrons is broken away from its position in the bonding structure such that it becomes free to move about in the lattice, a conduction electron is created and a broken bond, hole, is left behind. The energy required to break the bond is the band gap energy e.g. This model helps in visualizing the physical mechanism of electron-hole pair creation, but the energy band model is more productive for purposes of quantitative calculation. One important difficulty in the broken bond model is that the free electron and the hole seem deceptively localized in the lattice. Actually, the positions of the free electron and the hole are spread out over several lattice spacings and should be considered quantum mechanically by probability distributions, see section 2.4. Since the electrons and holes are created in pairs, the conduction band electron concentration n, electrons per cm3, is equal to the concentration of holes in the valence band P, holes per cm3. Each of these intrinsic carrier concentrations is commonly referred to as Ni. Thus for intrinsic material N equal P equal Ni, 3,6, at a given temperature there is a certain concentration of electron-hole pairs Ni. Obviously, if a steady state carrier concentration is maintained, there must be recombination of electron-hole pairs at the same rate at which they are generated. Recombination occurs when an electron in the conduction band makes a transition, direct or indirect, to an empty state, hole, in the valence band, thus annihilating the pair. If we denote the generation rate of electron-hole pairs as Gi, ehp/cm3 at S, and the recombination rate as Ri, equilibrium requires that each of these rates is temperature dependent. For example, Gi, T, increases when the temperature is raised, and a new carrier concentration Ni is established such that the higher recombination rate Ri, T, just balances generation. At any temperature, we can predict that the rate of recombination of electrons and holes Ri is proportional to the equilibrium concentration of electrons N0 and the concentration of holes. The factor Ar is a constant of proportionality which depends on the particular mechanism by which recombination takes place. We shall discuss the calculation of Ni as a function of temperature in section 3.3.3. Recombination processes will be discussed in chapter 4. Extrinsic material. In addition to the intrinsic carriers generated thermally, it is possible to create carriers in semiconductors by purposely introducing impurities into the crystal. This process, called doping, is the most common technique for varying the conductivity of semiconductors. By doping, a crystal can be altered so that it has a predominance of either electrons or holes. Thus there are two types of doped semiconductors, N-type, mostly electrons, and P-type, mostly holes. When a crystal is doped such that the equilibrium carrier concentrations N0 and P0 are different from the intrinsic carrier concentration Ni, the material is said to be extrinsic. When impurities or lattice defects are introduced into an otherwise perfect crystal, additional levels are created in the energy band structure, usually within the band gap. For example, an impurity from column V of the periodic table, phosphor, arsine, and antimony, introduces an energy level very near the conduction band in germanium or silicon. This level is filled with electrons at 0 K, and very little thermal energy is required to excite these electrons to the conduction band, Fig 312a. Thus at about 5100 kelvins virtually all of the electrons in the impurity level are donated to the conduction band. Such an impurity level is called a donor level, and the column V impurities in germanium or silicon are called donor impurities. From Fig 312a we note that the material doped with donor impurities can have a considerable concentration of electrons in the conduction band, even when the temperature is too low for the intrinsic electron-hole pairs concentration to be appreciable. Thus semiconductors doped with a significant number of donor atoms will have N0W, Ni, P0, at room temperature. This is N-type material. Figure 312 Energy band model and chemical bond model of dopants in semiconductors. A. Donation of electrons from donor level to conduction band. B. Acceptance of valence band electrons by an acceptor level, and the resulting creation of holes. C. Donor and acceptor atoms in the covalent bonding model of a silicon crystal. Atoms from column 3, boron, aluminum, gallium, and indium, introduce impurity levels in germanium or silicon near the valence band. These levels are empty of electrons at 0 K, Fig 312b. At low temperatures, enough thermal energy is available to excite electrons from the valence band into the impurity level, leaving behind holes in the valence band. Since this type of impurity level accepts electrons from the valence band, it is called an acceptor level, and the column 3 impurities are acceptor impurities in germanium and silicon. As Fig 312b indicates, doping with acceptor impurities can create a semiconductor with a hole concentration P0 much greater than the conduction band electron concentration N0. This type is P-type material. In the covalent bonding model, Donor and acceptor atoms can be visualized as shown in Fig 312c. An arsine atom, column 5, in the silicon lattice has the 4 necessary valence electrons to complete the covalent bonds with the neighboring silicon atoms, plus 1 extra electron. This 5th electron does not fit into the bonding structure of the lattice and is therefore loosely bound to the arsine atom. A small amount of thermal energy enables this extra electron to overcome its coulombic binding to the impurity atom and be donated to the lattice as a whole. Thus it is free to participate in current conduction. This process is a qualitative model of the excitation of electrons out of a donor level and into the conduction band, Fig 312a. Similarly, the column 3 impurity B has only 3 valence electrons to contribute to the covalent bonding, Fig 312c, thereby leaving one bond incomplete. With a small amount of thermal energy, this incomplete bond can be transferred to other atoms as the bonding electrons exchange positions. Again, the idea of an electron hopping from an adjacent bond into the incomplete bond at the B site provides some physical insight into the behavior of an acceptor, but the model of Fig 312b is preferable for most discussions. We can calculate rather simply the approximate energy required to excite the 5th electron of a donor atom into the conduction band, the donor binding energy. Let us assume for rough calculations that the As atom of Fig 312c has its 4 covalent bonding electrons rather tightly bound and the 5th extra electron loosely bound to the atom. We can approximate this situation by using the Bohr model results, considering the loosely bound electron as ranging about the tightly bound core electrons in a hydrogen-like orbit. From EQ 215, the magnitude of the ground state energy, n equal 1, of such an electron is. The value of K must be modified from the free space value for Pg0 used in the hydrogen atom problem to where Gr is the relative dielectric constant of the semiconductor material. In addition, we must use the conductivity effective mass m*n typical of the semiconductor, discussed in more detail in section 3.4.1. It was mentioned in section 3.2 that the covalent bonding model gives a false impression of the localization of carriers. As an illustration, calculate the radius of the electron orbit around the donor in Fig 312c, assuming a ground state hydrogen-like orbit in Si. Compare with the Si lattice constant. Use m*n equals 0.26 m0 for silicon. Solution from EQ 210, with n equal 1 and using gross equal 11.8 for silicon. Generally, the column 5 donor levels lie approximately 0.01 electron volts below the conduction band in germanium, and the column 3 acceptor levels lie about 0.01 electron volts above the valence band. In silicon, the usual donor and acceptor levels lie about 0.03–0.06 electron volts from a band edge. In 3,5 compounds, column 6 impurities occupying column 5 sites serve as donors. For example, sulfur, selenium, and tellurium are donors in gallium arsenide, since they substitute for arsenium and provide an extra electron compared with the arsine atom. Similarly, impurities from column 2, beryllium, zinc, cadmium, substitute for column 3 atoms to form acceptors in the 3,5 compounds. A more ambiguous case arises when a 3,5 material is doped with silicon or germanium, from column 4. These impurities are called amphoteric, meaning that silicon or germanium can serve as donors or acceptors depending on whether they reside on the column 3 or column 5 sublattice of the crystal. In gallium arsenide it is common for silicon impurities to occupy gallium sites. Since the silicon has an extra electron compared with the gallium it replaces, it serves as a donor. However, an excess of arsine vacancies arising during growth or processing of the gallium arsenide can cause silicon impurities to occupy arsine sites, where they serve as acceptors. The importance of doping will become obvious when we discuss electronic devices made from junctions between p-type and n-type semiconductor material. The extent to which doping controls the electronic properties of semiconductors can be illustrated here by considering changes in the sample resistance which occur with doping. In Si, for example, the intrinsic carrier concentration Ni is about 10 billion per cubic centimeter at room temperature. If we dope silicon with billion times million arsine atoms per cubic centimeter, the conduction electron concentration changes by 5 orders of magnitude. The resistivity of silicon changes from about 200,000 ohms per centimeter to 5 ohms per centimeter with this doping. When a semiconductor is doped N-type or P-type, one type of carrier dominates. In the example given above, the conduction band electrons outnumber the holes in the valence band by many orders of magnitude. We refer to the small number of holes in N-type material as minority carriers and the relatively large number of conduction band electrons as majority carriers. Similarly, electrons are the minority carriers in P-type material, and holes are the majority carriers. 3.2.5 Electrons and holes in quantum wells. We have discussed single-valued, discrete, energy levels in the band gap arising from doping, and a continuum of allowed states in the valence and conduction bands. A third possibility is the formation of discrete levels for electrons and holes as a result of quantum mechanical confinement. One of the most useful applications of molecular beam epitaxy, MBE, or organometallic vapor phase epitaxy, OMVPE, growth of multilayer compound semiconductors, as described in section 1.4, is the fact that a continuous single crystal can be grown in which adjacent layers have different band gaps. For example, Fig 3.13 shows the spatial variation in conduction and valence bands for a multi-layer structure in which a very thin layer of gallium arsenide is sandwiched between 2 layers of aluminum gallium arsenide, which has a wider band gap than the gallium arsenide. We will discuss the details of such heterojunctions, junctions between dissimilar materials, in section 5.8. It is interesting to point out here, however, that a consequence of confining electrons and holes in a very thin layer is that these particles behave according to the particle in a potential well problem in the confinement direction, with quantum states calculated in section 2.4.3. The particles are actually free to move in the other two directions, but we will ignore that for now. In section 8.4.6, we discuss that we form two-dimensional electron and hole gases in such quantum wells, leading to formation of subbands, rather than discrete quantum states as discussed here. Therefore, instead of having the continuum of states normally available in the conduction band electrons in the narrow gap material are confined to discrete quantum states as described by EQ 233, modified for effective mass and finite barrier height. Similarly, the states in the valence band available for holes are restricted to discrete levels in the quantum well. This is one of the clearest demonstrations of the quantum mechanical results discussed in Chapter 2. From a practical device point of view, the formation of discrete quantum states in the gallium arsenide layer of Fig 3.13 changes the energy at which photons can be emitted. An electron on one of the discrete conduction band states, E1 in Fig 3.13, can make a transition to an empty discrete valence band state in the gallium arsenide quantum well, such as E, giving off a photon of energy Eg plus E1 plus E, greater than the gallium arsenide band gap. Semiconductor lasers have been made in which such a quantum well is used to raise the energy of the transition from the infrared, typical of gallium arsenide, to the red portion of the spectrum. We will see other examples of quantum wells in semiconductor devices in later chapters. In calculating semiconductor electrical properties and analyzing device behavior, it is often necessary to know the number of charge carriers per cm3 in the material. The majority carrier concentration is usually obvious in heavily doped material, since one majority carrier is obtained for each impurity atom, for the standard doping impurities. The concentration of minority carriers is not obvious, however, nor is the temperature dependence of the carrier concentrations. To obtain equations for the carrier concentrations, we must investigate the distribution of carriers over the available energy states. This type of distribution is not difficult to calculate, but the derivation requires some background in statistical methods. Since we are primarily concerned here with the application of these results to semiconductor materials and devices, we shall accept the distribution function as given. The Fermi level. Electrons in solids obey Fermi-Dirac statistics 3. In the development of this type of statistics, one must consider the indistinguishability of the electrons, their wave nature, and the Pauli exclusion principle. The rather simple result of these statistical arguments is that the distribution of electrons over a range of allowed energy levels at thermal equilibrium is, where K is Boltzmann's constant. The function f, E, the Fermi-Dirac distribution function, gives the probability that an available energy state at E will be occupied by an electron at absolute temperature T. The quantity f is called the Fermi level, and it represents an important quantity in the analysis of semiconductor behavior. We notice that, for an energy E equal to the Fermi level energy f, the occupation probability is. Thus an energy state at the Fermi level has a probability of 1/2 of being occupied by an electron. A closer examination of f, E, indicates that at 0K the distribution takes the simple rectangular form shown in Fig 3.14. With t equals 0 in the denominator of the exponent, f, E, is 1/1 plus 0, equal 1 when the exponent is negative, E6f, and is 1/1 plus equal 0 when the exponent is positive, E7f. This rectangular distribution implies that at 0K every available energy state up to F is filled with electrons, and all states above F are empty. At temperatures higher than 0K, some probability exists for states above the Fermi level to be filled. For example, at T equal T1 in Fig 3.14 there is some probability F, E, that states above F are filled, and there is a corresponding probability 1, F, E, that states below F are empty. The Fermi function is symmetrical about F for all temperatures, that is, the probability F plus E, that a state E above F is filled is the same as the probability 1, F, E, that a state E below F is empty. The symmetry of the distribution of empty and filled states about F makes the Fermi level a natural reference point in calculations of electron and hole concentrations in semiconductors. In applying the Fermi-Dirac distribution to semiconductors, we must recall that F, E, is the probability of occupancy of an available state at E. Thus if there is no available state at E, for example, in the band gap of a semiconductor, there is no possibility of finding an electron there. We can best visualize the relation between F, E, and the band structure by turning the F, E, versus E diagram on its side so that the E scale corresponds to the energies of the band diagram, Fig 3.15. For intrinsic material we know that the concentration of holes in the valence band is equal to the concentration of electrons in the conduction band. Therefore, the Fermi level F must lie at the middle of the band gap in intrinsic material, for since F, E, is symmetrical about F, the electron probability tail of F, E, extending into the conduction band of Fig 3.15 is symmetrical with the hole probability tail 1, F, E, in the valence band. The distribution function has values within the band gap between EV and EC, but there are no energy states available, and no electron occupancy results from F, E, in this range. The tails in F, E, are exaggerated in Fig 3.15 for illustrative purposes. Actually, the probability values at EV and EC are quite small for intrinsic material at reasonable temperatures. For example, in Si at 300 K, Ni equal pi 10 cm, 3, whereas the densities of available states at EV and EC are on the order of 10-19 cm, 3. Thus the probability of occupancy F, E, for an individual state in the conduction band and the hole probability 1, F, E, for a state in the valence band are quite small. Because of the relatively large density of states in each band, small changes in F, E, can result in significant changes in carrier concentration. In N-type material there is a high concentration of electrons in the conduction band compared with the hole concentration in the valence band, recall Fig 3.12a. Thus in N-type material the distribution function F, E, must lie above its intrinsic position on the energy scale, Fig 3.15b. Since F, E, retains its shape for a particular temperature, the larger concentration of electrons at EC in N-type material implies a correspondingly smaller hole concentration at EV. We notice that the value of F, E, for each energy level in the conduction band, and therefore the total electron concentration N0, increases as F moves closer to EC. Thus the energy difference, EC, F, gives a measure of N. We shall express this relation mathematically in the following section. For p-type material the Fermi level lies near the valence band, Fig 315c, such that the 1, F, E, tail below EV is larger than the F, E, tail above EC. The value of F, EV, indicates how strongly p-type the material is. It is usually inconvenient to draw F, E, versus E on every energy band diagram to indicate the electron and hole distributions. Therefore, it is common practice merely to indicate the position of F in band diagrams. This is sufficient information, since for a particular temperature the position of F implies the distributions in Fig 315. 3.3.2 Electron and hole concentrations at equilibrium. The Fermi distribution function can be used to calculate the concentrations of electrons and holes in a semiconductor, if the densities of available states in the valence and conduction bands are known. For example, the concentration of electrons in the conduction band is where N, E, D is the density of states, centimeter, 3, in the energy range D. The subscript 0 used with the electron and hole concentration symbols, N0, P0, indicates equilibrium conditions. The number of electrons per unit volume in the energy range D is the product of the density of states and the probability of occupancy F, E. Thus the total electron concentration is the integral over the entire conduction band, as in EQ. 312. 5. The function N, E, can be calculated by using quantum mechanics and the Pauli exclusion principle, Appendix 4. It is shown in Appendix 4 that N, E, is proportional to E1 greater than 2, so the density of states in the conduction band increases with electron energy. On the other hand, the Fermi function becomes extremely small for large energies. The result is that the product F, E, N, E, decreases rapidly above EC, and very few electrons occupy energy states far above the conduction band H. Similarly, the probability of finding an empty state, hole, in the valence band 1, F, E, decreases rapidly below EV, and most holes occupy states near the top of the valence band. This effect is demonstrated in Fig 316, which shows the density of available states, the Fermi function, and the resulting number of electrons and holes occupying available energy states in the conduction and valence bands at thermal equilibrium, i.e., with no excitations except thermal energy. For holes, increasing energy points down in Fig 316, since the E scale refers to electron energy. The result of the integration of EQ 312 is the same as that obtained if we represent all of the distributed electron states in the conduction band by an effective density of states Nc located at the conduction band edge EC. Figure 316 schematic band diagram, density of states, Fermi-Dirac distribution, and the carrier concentrations for A, intrinsic, B, N-type, and C, P-type semiconductors at thermal equilibrium. Therefore, the conduction band electron concentration is simply the effective density of states at EC times the probability of occupancy at. In this expression we assume the Fermi level F lies at least several carat below the conduction band. Then the exponential term is large compared with unity, and the Fermi function F, EC, can be simplified as. Since carat at room temperature is only 0.026 eV, this is generally a good approximation. For this condition the concentration of electrons in the conduction band is N0 equal NCE, EC, F, carat, 315, the effective density of states is shown in Appendix 4 to be since the quantities in EQ 316a, are known, values of density of states can be tabulated as a function of temperature. as EQ 315 indicates, the electron concentration increases as F moves closer to the conduction band. This is the result we would predict from Fig 315b. In EQ 316a, m*n is the density of state's effective mass for electrons. To illustrate how it is obtained from the band curvature effective masses mentioned in section 3.2.2, let us consider the 6 equivalent conduction band minima along the x directions for silicon. Looking at the cigar-shaped equi-energy surfaces in Fig 310b, we find that we have more than one band curvature to deal with in calculating effective masses. There is a longitudinal effective mass milliliter along the major axis of the ellipsoid, and the transverse effective mass mt along the 2 minor axes. Since we have m*n 32 appearing in the density of states expression EQ 316a, by using dimensional equivalence and adding contributions from all 6 valleys, we get. It can be seen that this is the geometric mean of the effective masses. Calculate the density of states effective mass of electrons in silicon. For silicon, milliliter equals 0.98 m0, mount equals 0.19 m0 from Appendix 3. There are 6 equivalent X valleys in the conduction band. Note, for gallium arsenide, the conduction band equi-energy surfaces are spherical. So there is only one band curvature effective mass, and it is equal to the density of states effective mass, equals 0.067 m0. By similar arguments, the concentration of holes in the valence band is where NV is the effective density of states in the valence band. The probability of finding an empty state at EV is for F larger than EV by several carat. From these equations, the concentration of holes in the valence band is the effective density of states in the valence band reduced to the band edge is, as expected from Fig 315c, EQ 319, predicts that the hole concentration increases as F moves closer to the valence band. The electron and hole concentrations predicted by EQs 315 and 319 are valid whether the material is intrinsic or doped, provided thermal equilibrium is maintained. Thus for intrinsic material, F lies at some intrinsic level EI near the middle of the band gap, Fig 315a, and the intrinsic electron and hole concentrations are. The product of N0 and P0 at equilibrium is a constant for a particular material and temperature, even if the doping is varied. The intrinsic electron and hole concentrations are equal, since the carriers are created in pairs, Ni equal pi, thus the intrinsic concentration is the constant product of electron and hole concentrations in EQ 322. Can be written conveniently as. This is an important relation, and we shall use it extensively in later calculations. The intrinsic concentration for Si at room temperature is approximately Ni equals 15 billion per cubic centimeter. Comparing EQs 321 and 323, we note that the intrinsic level EI is the middle of the band gap, EC, EI equal Eg2, if the effective densities of states Nc and Nv are equal. There is usually some difference in effective mass for electrons and holes, however, and Nc and Nv are slightly different as EQs 316 and 320 indicate. The intrinsic level EI is displaced from the middle of the band gap, more for gallium arsenide than for germanium or silicon. Another convenient way of writing EQs 315 and 319 is obtained by the application of EQ 321. This form of the equations indicates directly that the electron concentrations is Ni when F is at the intrinsic level EI, and that N0 increases exponentially as the Fermi level moves away from EI toward the conduction band. Similarly, the hole concentration P0 varies from Ni to larger values as F moves from EI toward the valence band. Since these equations reveal the qualitative features of carrier concentration so directly, they are particularly convenient to remember. Silicon sample is doped with 1017 as atoms/centimeter 3. What is the equilibrium hole concentration P0 at 300 K? Where is F relative to EI? Since North Dakota WNI, we can approximate and from EQ 325A, we have temperature dependence of carrier concentrations. The variation of carrier concentration with temperature is indicated by EQ 325. Initially, the variation of N0 and P0 with T seems relatively straightforward in these relations. The problem is complicated, however, by the fact that Ni has a strong temperature dependence EQ 323, and that F can also vary with temperature. Let us begin by examining the intrinsic carrier concentration. By combining EQs 323, 316A, and 320, we obtain the exponential temperature dependence dominates Ni, T, and a plot of ln Ni versus 103 T appears linear, Fig 317. 7. In this figure we neglect variations due to the T3 greater than 2 dependence of the density of states function and the fact that G varies somewhat with temperature. 8. The value of Ni at any temperature is a definite number for a given semiconductor, and is known for most materials. Thus we can take Ni as given in calculating N0 or P0 from EQ 325, 9. With Ni and T given, the unknowns in EQ 325 are the carrier concentrations and the Fermi level position relative to EI. One of these two quantities must be given if the other is to be found. If the carrier concentration is held at a certain value, as in heavily doped extrinsic material, F can be obtained from EQ 325. The temperature dependence of electron concentration in a doped semiconductor can be visualized as shown in Fig 318. In this example, Si is doped N-type with a donor concentration of million times billion per cubic centimeter. At very low temperatures, large 1T, negligible intrinsic electron-hole pairs exist, and the resulting band diagram is. When plotting quantities such as carrier concentration, which involve a Boltzmann factor, it is common to use an inverse temperature scale. This allows terms which are exponential in 1/t to appear linear in the semi-logarithmic plot. When reading such graphs, remember that temperature increases from right to left. 8 FORSI The band gap Eg varies from about 1.11 eV at 300 K to about 1.16 eV at 0 K. 9 CARE must be taken to use consistent units in these calculations. For example, if an energy such as Eg is expressed in electron volts, eV, it should be multiplied by Q, 1.6 10, 19 C, to convert to joules if K is in J/K. Alternatively, Eg can be kept in eV and the value of K in eV/K can be used. At 300 K we can use Figure 317. Intrinsic carrier concentration for germanium, silicon, and gallium arsenide as a function of inverse temperature. The room temperature values are marked for reference. The donor electrons are bound to the donor atoms. The temperature is raised, these electrons are donated to the conduction band, and at about 100 K, 1000 T equal 10, all the donor atoms are ionized. This temperature range is called the ionization region. Once the donors are ionized, the conduction band electron concentration is N0. 1 million times billion donor atoms per cubic centimeter, since one electron is obtained for each donor atom. When every available extrinsic electron has been transferred to the conduction band, N0 is virtually constant with temperature until the concentration of intrinsic carriers Ni becomes comparable to the extrinsic concentration of donors. Finally, at higher temperatures Ni is much greater than number of donors, and the intrinsic carriers dominate. In most devices it is desirable to control the carrier concentration by doping rather than by thermal EHP generation. Thus one usually dopes the material such that the extrinsic range extends beyond the highest temperature at which the device is to be used. Figure 318 Carrier concentration versus inverse temperature for silicon doped with 1015 donors/centimeter 3. Compensation and space charge neutrality. When the concept of doping was introduced, we assumed the material contained either N donors or N acceptors, so that the extrinsic majority carrier concentrations were N0. Donors or charge carriers. Acceptors, respectively, for the N-type or P-type material. It often happens, however, that a semiconductor contains both donors and acceptors. For example, Fig 319 illustrates a semiconductor for which both donors and acceptors are present, but the predominance of donors makes the material N-type, and the Fermi level is therefore in the upper part of the band gap. Since F is well above the acceptor level Ea, this level is essentially filled with electrons. However, with F above Ei, we cannot expect a whole concentration in the valence band. Figure 319. Compensation in an N-type semiconductor. Commensurate with the acceptor concentration. In fact, the filling of the Ea states occurs at the expense of the donated conduction band electrons. The mechanism can be visualized as follows: assume an acceptor state is filled with a valence band electron as described in Fig 312b, with a hole resulting in the valence band. This hole is then filled by recombination with one of the conduction band electrons. Extending this logic to all the acceptor atoms, we expect the resultant concentration of electrons in the conduction band to be donors and acceptors instead of the total donors. This process is called compensation. By this process it is possible to begin with an N-type semiconductor and add acceptors until number of acceptors equals number of donors and no donated electrons remain in the conduction band. In such compensated material, N0 equal Ni equal P0 and intrinsic conduction is obtained. With further acceptor doping, the semiconductor becomes P-type with a whole concentration of essentially acceptors donors. The exact relationship among the electron, hole, donor, and acceptor concentrations can be obtained by considering the requirements for space charge neutrality. If the material is to remain electrostatically neutral, the sum of the positive charges, holes and ionized donor atoms, must balance the sum of the negative charges, electrons and ionized acceptor atoms. P0 plus donors plus equal N0 plus acceptors, 327. Thus in Fig 319 the net electron concentration in the conduction band is N0 equal P0 plus, donors plus, acceptors, 328. If the material is doped N-type and all the impurities are ionized, we can approximate EQ 328 by donors, acceptors. Since the intrinsic semiconductor itself is electrostatically neutral and the doping atoms we add are also neutral, the requirement of EQ 327 must be maintained at equilibrium. The electron and hole concentrations and the Fermi level adjust such that EQs 327 and 325 are satisfied. Knowledge of carrier concentrations in a solid is necessary for calculating current flow in the presence of electric or magnetic fields. In addition to the values of N and P, we must be able to take into account the collisions of the charge carriers with the lattice and with the impurities. These processes will affect the ease with which electrons and holes can flow through the crystal, that is, their mobility within the solid. As should be expected, these collision and scattering processes depend on temperature, which affects the thermal motion of the lattice atoms and the velocity of the carriers. Conductivity and mobility. The charge carriers in a solid are in constant motion, even at thermal equilibrium. At room temperature, for example, the thermal motion of an individual electron may be visualized as random scattering from lattice vibrations, impurities, other electrons, and defects, Fig 320a. Since the scattering is random. Figure 320. A. Random thermal motion of an electron in a solid. B. Well-directed drift velocity with an applied electric field. there is no net motion of the group of n electrons/centimeter 3 over any period of time. This is not true of an individual electron, of course. The probability of the electron in Fig 320 returning to its starting point after some time t is negligibly small. However, if a large number of electrons is considered, for example, 10^16 centimeter 3 in an n-type semiconductor, there will be no preferred direction of motion for the group of electrons and no net current flow. If an electric field X is applied in the x direction, each electron experiences a net force, Qx from the field. This force may be insufficient to alter appreciably the random path of an individual electron. The effect when averaged over all the electrons, however, is a net motion of the group in the x direction, Fig 320b. If px is the x component of the total momentum of the group, the force of the field on the n electron/centimeter 3 is nqx equal dpx dt field, 329. Initially, EQ 329 seems to indicate a continuous acceleration of the electrons in the x direction. This is not the case, however, because the net acceleration of EQ 329 is just balanced in steady state by the decelerations of the collision processes. Thus, while the steady field x does produce a net momentum px, the net rate of change of momentum when collisions are included must be zero in the case of steady state current flow. To find the total rate of momentum change from collisions, we must investigate the collision probabilities more closely. If the collisions are truly random, there will be a constant probability of collision at any time for each electron. Let us consider a group of n0 electrons at time t equals 0 and define n, t, as the number of electrons that have not undergone a collision by time t. The rate of decrease in n, t, at any time t is proportional to the number left unscattered at t, where t-1 is a constant of proportionality. The solution to EQ 330 is an exponential function, and t represents the mean time between scattering events, 10 called the mean free time. The probability that any electron has a collision in the time interval dt is dtt. Thus the differential change in px due to collisions in time dt is. The rate of change of px due to the decelerating effect of collisions is. The sum of acceleration and deceleration effects must be zero for steady state. Taking the sum of EQs 329 and 333, we have, where the angular brackets indicate an average over the entire group of electrons. As expected for steady state, EQ 335 indicates that the electrons have on the average a constant net velocity in the negative x direction. Actually, the individual electrons move in many directions by thermal motion during a given time period, but EQ 336 tells us the net drift of an average electron in response to the electric field. The drift speed described by EQ 336 is usually much smaller than the random speed due to the thermal motion Vth. The current density resulting from this net drift is just the number of electrons crossing a unit area per unit time, N8 Vx9, multiplied by the charge. On the electron, Q, 10 equations, 330, and 331, are typical of events dominated by random processes, and the forms of these equations occur often in many branches of physics and engineering. For example, in the radioactive decay of unstable nuclear isotopes, N0 nuclides decay exponentially with a mean lifetime t. Other examples will be found in this text, including the absorption of light in a semiconductor and the recombination of excess electron-hole pairs. Using EQ 336, for the average velocity, we obtain. Thus the current density is proportional to the electric field, as we expect from Ohm's law, where the conductivity can be written, where the quantity Mn, called the electron mobility, describes the ease with which electrons drift in the material. Mobility is a very important quantity in characterizing semiconductor materials and in device development. Here m*n is the conductivity effective mass for electrons, different from the density of states effective mass mentioned in EQ 316b. While we use the density of states effective mass to count the number of carriers in bands, we must use the conductivity effective mass for charge transport problems. To illustrate how it is obtained from the band curvature effective masses mentioned in section 3.2.2, once again let us consider the 6 equivalent conduction band minima along the x directions for SI, with the band curvature longitudinal effective mass, milliliter, along the major axis of the ellipsoid, and the transverse effective mass, mount, along the 2 minor axes, Fig 310b. Since we have one m*n in the mobility expression EQ 340a, by using dimensional equivalence, we can write the conductivity effective mass as the harmonic mean of the band curvature effective masses. Calculate the conductivity effective mass of electrons in SI. There are 6 equivalent x values in the conduction band. Note, for GAAS, the conduction band equi-energy surfaces are spherical. So there is only one band curvature effective mass. The density of states effective mass and the conductivity effective mass are both 0.067 m0. The mobility defined in EQ 340a can be expressed as the average particle drift velocity per unit electric field. Comparing EQs 336 and 340a, we have the unit of mobility is centimeter/s, v/centimeter, equals centimeter 2/v at s, as EQ 341 suggests. The minus sign in the definition results in a positive value of mobility, since electrons drift opposite to the field. The current density can be written in terms of mobility as. This derivation has been based on the assumption that the current is carried primarily by electrons. For hole conduction we change N to P, Q to plus Q, and on to op, where op equal plus 8Vx9x is the mobility for holes. If both electrons and holes participate, we must modify EQ 342, to. Values of on and op are given for many of the common semiconductor materials in Appendix 3. According to EQ 340, the parameters determining mobility are m** and mean free time t. Effective mass is a property of the material's band structure, as described by EQ 33. Thus we expect m** n to be small in the strongly curved minimum of the gallium arsenide conduction band, Fig 3.6, with the result that on is very high. In a more gradually curved band, a larger m** in the denominator of EQ 340, leads to a smaller value of mobility. It is reasonable to expect that lighter particles are more mobile than heavier particles, which is satisfying, since the common sense value of effective mass is not always apparent. The other parameter determining mobility is the mean time between scattering events, t. In section 3.4.3 we shall see that this is determined primarily by temperature and impurity. Concentration in the semiconductor. Drift and resistance. Let us look more closely at the drift of electrons and holes. If the semiconductor bar of Fig 321 contains both types of carrier, EQ 343, gives the conductivity of the material. The resistance of the bar is then. Where R is the resistivity? Centimeter. The physical mechanism of carrier drift requires that the holes in the bar move as a group in the direction of the electric field and that the electrons move as a group in the opposite direction. Both the electron and the hole components of current are in the direction of the field, since conventional current is positive in the direction of hole flow and opposite to the direction of electron flow. The drift current described by EQ 343 is constant throughout the bar. A valid question arises, therefore, concerning the nature of the electron and hole flow at the contacts and in the external circuit. We should specify that the contacts to the bar of Fig 321 are ohmic, meaning that they are perfect sources and sinks of both carrier types and have no special tendency to inject or collect either electrons or holes. If we consider that current is carried around the external circuit by electrons, there is no problem in visualizing electrons flowing into the bar at one end and out at the other, always opposite to I. Thus for every electron leaving the left end, x equals 0, of the bar in Fig 321, there is a corresponding electron entering at x equal L, so that the electron concentration in the bar remains constant at n. But what happens to the holes at the contacts? As a hole reaches the ohmic contact at x equal L, it recombines with an electron, which must be supplied through the external circuit. As this hole disappears, a corresponding hole must appear at x equals 0 to maintain space charge. Figure 321. Drift of electrons and holes in a semiconductor bar. Neutrality. It is reasonable to consider the source of this hole as the generation of an electron-hole pairs at x equals 0, with the hole flowing into the bar and the electron flowing into the external circuit. Effects of temperature and doping on mobility. The two basic types of scattering mechanisms that influence electron and hole mobility are lattice scattering and impurity scattering. In lattice scattering, a carrier moving through the crystal is scattered by a vibration of the lattice. Resulting from the temperature 11, the frequency of such scattering events increases as the temperature increases, since the thermal agitation of the lattice becomes greater. Therefore, we should expect the mobility to decrease as the sample is heated, Fig 322. On the other hand, scattering from crystal defects such as ionized impurities becomes the dominant mechanism at low temperatures. Since the atoms of the cooler lattice are less agitated, lattice scattering is less important. However, the thermal motion of the carriers is also slower. Since a slowly moving carrier is likely to be scattered more strongly by an interaction with a charged ion than is a carrier with greater momentum, impurity scattering events cause a decrease in mobility with decreasing temperature. As Fig 322 indicates, the approximate temperature dependencies are T-3 greater than 2 for lattice scattering and T3 greater than 2 for impurity scattering. Since the scattering probability of EQ 332 is inversely proportional to the mean free time and therefore to mobility, the mobilities due to two or more scattering mechanisms add inversely. Figure 322 approximate temperature dependence of mobility with both lattice and impurity scattering. Collective vibrations of atoms in the crystal are called phonons. Thus lattice scattering is also known as phonon scattering. As a result, the mechanism causing the lowest mobility value dominates, as shown in Fig 322. As the concentration of impurities increases, the effects of impurity scattering are felt at higher temperatures. For example, the electron mobility on of intrinsic silicon at 300 K is 1350 square centimeters, V at S. With a donor doping concentration of 1017 centimeter, 3, however, on is 700 square centimeters, V at S. Thus, the presence of the 1017 ionized donors/centimeter 3 introduces a significant amount of impurity scattering. This effect is illustrated in Fig 323, which shows the variation of mobility with doping concentration at room temperature. Figure 323. Variation of mobility with total doping impurity concentration, acceptors plus donors, for germanium, silicon, and gallium arsenide at 300 K. Example 37, A silicon bar 1 ohm long and 100 ohm2 in cross-sectional area is doped with 1017 cm, 3 phosphorus. Find the current at 300 K with 10 V applied. B. How long does it take an average electron to drift 1 ohm in pure silicon at an electric field of 100 V/cm? Repeat for 105 V/cm. Find the current at 300 K with 10 V applied for a SI bar 1 ohm long, 100 ohm2 in cross-sectional area, and doped with 1017 cm, 3 phosphorus. High field effects. One assumption implied in the derivation of EQ 339 was that Ohm's law is valid in the carrier drift processes. That is, it was assumed that the drift current is proportional to the electric field and that the proportionality constant, S, is not a function of field. This assumption is valid over a wide range of. However, large electric fields, 703 v/centimeter, can cause the drift velocity and therefore the current J equal QNVD to exhibit a sublinear dependence on the electric field. This dependence of S upon is an example of a hot carrier effect, which implies that the carrier drift velocity Vd is comparable to the thermal velocity Vth. In many cases an upper limit is reached for the carrier drift velocity in a high field, Fig 324. This limit occurs near the mean thermal velocity, 107 cm/s, and represents the point at which added energy imparted by the field is transferred to the lattice rather than increasing the carrier velocity. The result of this scattering limited velocity is a fairly constant current at high field. This behavior is typical of silicon, germanium, and some other semiconductors. However, there are other important effects in some materials. For example, in Chapter 10 we shall discuss a decrease in electron velocity at high fields for gallium arsenide and certain other materials, which results in negative conductivity and current instabilities in the sample. Another important high field effect is avalanche multiplication, which we shall discuss in section 5.4.2. The Hall effect. If a magnetic field is applied perpendicular to the direction in which holes drift in a p-type bar, the path of the holes tends to be deflected, Fig 325. Using vector notation, the total force on a single hole due to the electric and magnetic fields is. The important result of EQ 347 is that unless an electric field EY is established along the width of the bar, each hole will experience a net force, and therefore an acceleration, in the y direction due to the QVXBZ product. Therefore, to maintain a steady state flow of holes down the length of the bar, the electric field EY must just balance the product VXBZ, so that the net force Fy is zero. Physically, this electric field is set up when the magnetic field shifts the hole distribution slightly in the y direction. Once the electric field EY becomes as large as VXBZ, no net lateral force is experienced by the holes as they drift along the bar. The establishment of the electric field EY is known as the Hall effect, and the resulting voltage VAB equal I is called the Hall voltage. If we use the expression derived in EQ 337, for the drift velocity, using plus Q and P0 for holes, the field EY becomes. Thus the Hall field is proportional to the product of the current density and the magnetic flux density. The proportionality constant RH equal, QP0, 1 is called the Hall coefficient. A measurement of the Hall voltage for a known current and magnetic field yields a value for the hole concentration P0. Since all of the quantities in the right-hand side of EQ 350 can be measured, the Hall effect can be used to give quite accurate values for carrier concentration. If a measurement of resistance R is made, the sample resistivity R can be calculated. Since the conductivity S equal 1/R is given by QMPP0, the mobility is simply the ratio of the Hall coefficient and the resistivity. Measurements of the Hall coefficient and the resistivity over a range of temperatures yield plots of majority carrier concentration and mobility versus temperature. Such measurements are extremely useful in the analysis of semiconductor materials. Although the discussion here has been related to p-type material, similar results are obtained for n-type material. A negative value of Q is used for electrons, and the Hall voltage VAB and Hall coefficient RH are negative. In fact, measurement of the sign of the Hall voltage is a common technique for determining if an unknown sample is p-type or n-type. Referring to Fig 325, consider a semiconductor bar with W equals 0.1 mm, example 3A T equal 10 ohm, and L equal 5 mm. For B equal 10 kg in the direction shown, 1 kg equal 10 to 5 Wb/cm², and a current of 1 mA, we have VAB equal -2 mV. And VCD equal 100 mV. Find the type, concentration, and mobility of the majority carrier. From the sign of VAB, we can see that the majority carriers are electrons. In this chapter we have discussed homogeneous semiconductors, without variations in doping and without junctions between dissimilar materials. In the following chapters we will be considering cases in which non-uniform doping occurs in a given semiconductor, or junctions occur between different semiconductors or a semiconductor and a metal. These cases are crucial to the various types of electronic and optoelectronic devices made in semiconductors. In anticipation of those discussions, an important concept should be established here regarding the demands of equilibrium. That concept can be summarized by noting that no discontinuity or gradient can arise in the equilibrium Fermi level F. To demonstrate this assertion, let us consider two materials in intimate contact such that electrons can move between the two, Fig 326. These may be, for example, dissimilar semiconductors, N and P-type regions, a metal and a semiconductor, or simply two adjacent regions of a non-uniformly doped semiconductor. Each material is described by a Fermi-Dirac distribution function and some distribution of available energy states that electrons can occupy. Figure 326. Two materials in intimate contact at equilibrium. Since the net motion of electrons is zero, the equilibrium Fermi level must be constant throughout. There is no current, and therefore no net charge transport, at thermal equilibrium. There is also no net transfer of energy. Therefore, for each energy E in Fig 326, any transfer of electrons from material 1 to material 2 must be exactly balanced by the opposite transfer of electrons from 2 to 1. We will let the density of states at energy E in material 1 be called N1, E, and in material 2 we will call it N2, E. At energy E the rate of transfer of electrons from 1 to 2 is proportional to the number of filled states at E in material 1 times the number of empty states at E in material 2. Where F, E, is the probability of a state being filled at E in each material. That is, the Fermi-Dirac distribution function given by EQ. 310. Similarly, at equilibrium these must be equal. Rearranging terms, we have, at energy E, which results in. Therefore, we conclude that EF1 equal EF2. That is, there is no discontinuity in the equilibrium Fermi level. More generally, we can state that the Fermi level at equilibrium must be constant throughout materials in intimate contact. One way of stating this is that no gradient exists in the Fermi level at equilibrium. We will make considerable use of this result in the chapters to follow. 3.1 In a diamond lattice, each Si atom, with 4 valence electrons, is surrounded by 4 silicon atoms that form 4 covalent bonds consisting of shared electron pairs, thereby forming an octet of electrons in the valence shell. In zinc blende structures such as gallium arsenide, electrons are partly shared, covalent bonding, and partly transferred from gallium to arsenide, ionic bonding. 3.2 In crystals, electronic wave functions overlap to give various linear combinations of atomic orbitals, LCAO. Bonding or symmetric combinations of the wave functions of valence shell electrons form, almost, continuous allowed bands of energies in the, almost, filled valence band, separated by an energy gap from higher energy states in an, almost, empty conduction band that correspond to the anti-bonding or anti-symmetric LCAOs. Empty electronic states in the valence band can be considered to be positively charged carriers, holes, while filled states in the conduction band are negatively charged, conduction, electrons. 3.3 If the band gaps are large, we get insulators; if they are small, 1 eV, we get semiconductors, and if they are 0, we get conductors, metals. 3.4 Simplified band diagrams plot electron energy in the conduction band, increasing upward, as a function of position. The band edge corresponds to potential energy, and the distance from the band edge gives the kinetic energy. Hole energies increase downward in the valence band. 3.5 Carrier energies can also be plotted as a function of wave vector k, proportional to velocity or momentum, to give, E, k, band structures, which can be direct, conduction band minimum directly above valence band maximum, or indirect. The curvature of the E, K, is inversely proportional to the effective mass m** of the carriers. The m* accounts for the interactions of the carriers with the periodic crystal potential. 3.6 In a pure semiconductor, we have an intrinsic concentration of electrons, or holes, Ni, that result from thermal generation recombination between the valence and conduction band, or bond breaking. If we replace some Si atoms, with 4 valence electrons, with donor impurities with 5 valence electrons, they donate conduction electrons, donors. Similarly, acceptors create holes. P3.7 The number of electrons, N, is the integral with respect to energy from the bottom to the top of the conduction band of the product of the available density of states, DOS, and the Fermi-Dirac, FD, distribution function. For parabolic band structures, we get a parabolic DOS. The FD function is the average occupancy of an electronic state. The electron concentration N can also be expressed as the product of an effective DOS at the band edge and the FD occupancy at EC, and similarly for holes P. The NP product in equilibrium is constant, Ni2. 3.8 Electrons in a solid execute random Brownian motion with an average kinetic energy related to the thermal energy carried. In an electric field, electrons drift, on top of the random motion, with a velocity equal to mobility times field in the ohmic regime and saturation velocity at high fields. The drift current is proportional to carrier concentration times drift velocity. Negatively charged electrons drift opposite to the electric field, and the current is opposite to the motion. Positively charged holes drift in the direction of the electric field, and the current goes in the same direction as the hole flow. 3.9 Carrier mobility is determined by scattering, caused by deviations from a periodic lattice potential, such as lattice vibrations, phonons, or ionized impurities. Carrier mobility and concentration can be obtained by the Hall effect and resistivity measurements.